Let me make an illustration of what I mean by the average location of mass. Take this golf club for example. Where could I balance it from? Where's the balancing point? You know, that's a little tough. Let me go to something you're a little more familiar with. Check out this meter stick. Now this meter stick is something you have seen before and would make real good first example to asking the question, where is the center of mass? If you said right in the middle, you would be right. Now this is straightforward because you know that the meter stick is symmetrical on all its sides, which means the distribution of mass within this piece of wood is pretty uniform. And we call that uniform mass distribution. If the mass is uniformly distributed, then the average location of mass is going to be right in the middle. Let me show you a cool trick on how to figure this out. If you were to take this stick and balance it on your index fingers like this, and bring your fingers together slowly, your fingers will touch at the center of mass. Great! I've taken both of these balls and massed them on a digital balance. And I came up with the foam ball having a mass of 23.6 grams. That means that the mass in kilograms is 0.0236 kilograms. Now the mass of the tennis ball on the digital balance was 56.5 grams, and that means it is 0.0565 kilograms. So I used a digital balance to get these masses, and now we're in good shape. Now we are going to neglect the mass of the rod because the mass of the rod is insignificant to the mass of these balls right here. Okay, well, using our qualitative demonstration here, we determined that the center of mass was located right here on this black mark. So I went also ahead and put that black mark there so you could see that. So that's where we determine qualitatively the center of gravity to be. Well, how about quantitatively? How about using numbers, like the relationship that's up here behind us? Well, in order to do that, we need to establish a frame of reference, a place to say, from this point, the center of gravity is this. Well, we're going to go ahead and use this XY coordinate axis system. Now, it's always good to put the origin on one of the objects, because at the center of mass of the object will, let me start that over. When the origin is at the center of the object, the mass's center of gravity will be at that point. That right there is a catchphrase. If the ball, and these balls are, uniformly distributed, then the center of mass will be at the dead center of these balls. And we're not going to work with an object right now that has a non-uniform mass distribution. Recall that the golf club has a non-uniform mass distribution. The baseball bat has a non-uniform mass distribution. The ski has a non-uniform mass distribution. Another uniform mass distribution that we used was the meter stick. Now this piece of wood, as it went, from 0 to 100 centimeters, all of the wood was distributed evenly throughout. And that put the center of mass right on 50. So we're going to consider the origin of the tennis ball to be the center of gravity of that ball. Now that's going to help us out when we measure or sum up the average location of the tennis ball's mass. Okay, well, we're going to put the origin on the tennis ball. That means we need to determine, we have to know, in order to use this expression, the center of mass, all our mass is on the x-axis, so the center of mass will be the sum of the average locations divided by the total mass. Okay, great. Well, we know that this location right here is 0, 0. So that's its location. And what about the foam ball? Well, let's put the origin right on the center of the ball, and look at where the center of mass of the ball is located. And so from my point right here, I see it being located at about 55 centimeters. 55 centimeters. So that's what we're going to work off of. It has a position of 0.55 meters, 0. All right, cool. Well, we have all our information now. So, in order to determine the center of mass, it will be the mass of the tennis ball, which is 0.0565 kilograms times 0. Now, 0 meters because it's on the origin, plus the mass of the foam ball, which is 0.0236 kilograms times its position of positive 0.55 meters. And then we're going to divide all of that by the sum of the masses of the two balls. And that means 0.0565 kilograms plus 0.0236 kilograms. And let's see what that gives us. Now we see that this term just goes right away because it's multiplied by 0. That's helpful. And that then gives us an answer of 0.0236 times 0.55. And we're going to divide that by the sum of the two. So 0.0565 plus 0.0236. And coming through, we end up with 0.16 meters. Positive. That is a positive value. So, our center of mass, we are quantitatively defining as being 16 centimeters from this location. So this was 55 centimeters, so we are in the region here. This should be 16 centimeters, right around in here. So let's see if that is indeed what pans out here. I'm reading our black spot at 17, exactly 17 centimeters. So you can see that we are pretty doggone close. It's just a simple measurement, making some general assumptions. One assumption is that the mass of the balls are uniformly distributed. Our second assumption is that the rod is light enough such that it contributes or it doesn't contribute any mass. So I'm happy with the application. From a qualitative point of view, we show it here. We end up about 1 centimeter off from our qualitative measurement and our quantitative measurement. But if you are able to understand that these are point masses, then this train of thought for determining the center of mass is all there is to it. It gets a little bit more involved when the mass, however, is not uniformly distributed. Now, we are not going there. That is beyond the scope of this course and this lesson, but this is the basic concept of determining quantitatively the center of mass.